Welcome everyone, my name is Thijs Vlucht. Today I will discuss with you some important heat pump applications. The learning objectives of this video are as follows. We first review and repeat the vapor compression refrigeration cycle that we discussed last lecture. I will briefly introduce the software RefProp, which is a very nice reference tool for obtaining thermodynamic properties of working fluids. After that, I will briefly discuss the concept of exergy, and finally we will make an exercise in which we calculate both the first law efficiency as well as the second law efficiency of a compressor. Last lecture we discussed the vapor compression refrigeration cycle, which is used to transfer heat from a cold body to a hot body by transformations of a working fluid, also called refrigerant. In the evaporator, the working fluid is fully evaporated, taking heat from the surrounding, in this case the cold region. At the end of the evaporator, state 1, the working fluid leaves as a saturated vapor. In the compressor, the saturated vapor is compressed isentropically, in the ideal situation, to a higher pressure state 2 or state 2s. S is here to indicate isentropic conditions. This compression causes an increase in temperature. The high pressure working fluid is condensed in the condenser, thereby releasing heat to the warm region. At the end of the condenser, point 3, all the vapor is condensed to a liquid and the working fluid is now a saturated liquid. In an expansion valve, the pressure is reduced to that of the cold region, state 4, and the working fluid is partially evaporated, after which the cycle starts again in the evaporator. In the TS diagram on the left, the thermodynamic states 1, 2, 3 and 4 are illustrated. The net effect of this cycle is that due to the work of the compressor, heat is transformed from a low temperature to a high temperature. The coefficient of performance, COP, is defined as the usual effect, heating or cooling, depending on whether we must deal with a heat pump or refrigerator, divided by the work of the compressor. The maximum possible efficiency is the Carnot efficiency, which only depends on the temperatures of the hot region and the cold region. The so-called second law efficiency is defined as the ratio of the actual coefficient of performance and the coefficient of performance of the corresponding Carnot cycle. Note that the equations for this are defined slightly different depending on what we call the useful effect. Let us now make an exercise to compute the coefficient of performance, COP, of an actual vapor compression refrigeration cycle. The refrigerant is called R134A, which is a common refrigerant. The thermodynamic properties of the refrigerant can be obtained using the RefProp software, which can be obtained from NIST. A demonstration version of this software can be downloaded for free. There are also open source and free alternatives such as CoolProp. In RefProp, we first select the working fluid R134A and we select the unit Celsius for temperature and kilopascal for pressure. The exercise is as follows. R134A enters the compressor of a vapor compression refrigeration cycle at 120 kilopascal and as a saturated vapor and leaves at 900 kilopascal and 75 degrees Celsius. The refrigerant leaves the condenser as a saturated liquid. The rate of cooling provided by the system is given and this is equal to 5.275 kilowatt. We are asked to calculate A, the mass flow rate of the refrigerant and B, the COP of the cycle. To solve this, we start with the working fluid at the start of the compressor. It is a saturated vapor and the pressure is given as 120 kilopascal. So in the table for properties of the saturated points, we will be at 120 kilopascal and we immediately obtain the enthalpy in point 1. This is 385.12 kilojoule per kilogram. The conditions at the end of the compressor are also given, 900 kilopascal and 75 degrees Celsius. We go to the table of the specific state points and we fill in the temperature and pressure, and we obtain the enthalpy at point 2, which is equal to 458.66 kilojoule per kilogram. We assume that there is no pressure drop in the condenser. At the end of the condenser, the working fluid leaves as a saturated liquid, and we can immediately get the enthalpy at point 3 from the saturation tables, which is 249.78 kilojoule per kilogram. The mass flow can now be calculated from the cooling rate, which is given and equal to 5.275 kilowatt, and that is equal to 5.275 kilojoule per second, divided by the difference in specific enthalpy for the evaporator, which is equal to H1 minus H4 in units of kilojoule per kilogram. This results in a mass flow rate of 0.039 kilogram per second. The coefficient of performance is the cooling rate, H1 minus H4, divided by the mechanical work of the compressor, H2 minus H1, which results in a COP of 1.84, which is a lot larger than 1. The first law of thermodynamics states that energy cannot be destroyed, and energy can only be converted from one source to another source. However, some forms of energy are useful and other ones are not. Hence, we need to define the quality of energy. This is what we mean by the quantity exergy. Consider, for example, an isolated system that cannot exchange heat with the surroundings. In this closed system, there is air and fuel. If we burn all the fuel, then the air will be a bit hotter. As the system is isolated, the total energy of the system is the same before or after the fuel was burned. However, the economic value of the system has decreased by burning all the fuel, because in principle we could have obtained mechanical work, which is useful. It can, for example, be converted into electricity. The hot air has little economic value, as it is very difficult and not economic to extract energy from this. The quality exergy is used to define the quality of energy. It is formally defined as the maximum theoretical work obtainable from an overall system and environment as the system comes into equilibrium with the environment. By reaching this, the system is in the so-called dead state. Exergy quantifies the potential for use, the maximum theoretical work, and it can be transferred from and to systems. It is important to note that exergy can be destroyed by irreversibilities of friction in the system. Having zero exergy destruction is not possible in practice, as it only applies to processes that are infinitely slow. It is the task of an engineer to make sure that the exergy destruction of a system is minimal given a certain production rate of the system. Exergy destruction is closely related to entropy production in the system. Multiplying the entropy production with the surrounding temperature T0 gives the exergy destruction. For a heat pump, we can quantify the exergy destruction for each part of the heat pump cycle in the so-called Sankey diagram. The work provided by the compressor is pure exergy. A part of this exergy is lost due to irreversible processes in the compressor, the evaporator, condenser and the valve. But if correct, a large part of this provided exergy is used as a useful effect, the heating or the cooling, depending on whether we deal with a heat pump or a refrigerator. For the design of a heat pump, it is essential to perform an exergy analysis for all of the components in the system to see where there are losses so that the large losses can be mitigated. As an example, we consider the calculation of the exergy destruction and the second law efficiency of a compressor. This exercise is as follows. Refrigerant R134A at minus 20 degrees Celsius enters a compressor as a saturated vapor with a flow rate of 0.45 kilogram per second and leaves at 800 kilopascal and 45 degrees Celsius. Assume the heat loss to the surrounding air from the compressor is 10% of the work input to the compressor. We are asked to calculate A, the compressor work, and B, the amount of heat loss, and C, the exergy destruction, and D, the energy and exergy efficiencies of the compressor. We should take T0 as 25 degrees Celsius, which can be taken as the boundary or surface temperature of the compressor. How to solve this? Again, we use RefProp to obtain thermodynamic properties of this refrigerant. The refrigerant enters the compressor as a saturated liquid at minus 20 degrees Celsius, so in the saturation table in RefProp we can immediately look up the enthalpy and entropy production at the inlet state point 1. These are H1 is 386.55 kJ per kilogram and S1 equals 1.7413 kJ per kilogram. At the outlet, the temperature is 45 degrees Celsius and the pressure is 800 kilopascal. So with RefProp, we find the enthalpy and entropy at the outlet of the compressor. These are H2 is 429.74 kJ per kilogram and S2 is 1.7599 kJ per kilogram Kelvin. The first law of thermodynamics for an open system in a stationary state equals W is Q plus M times H1 minus H2, in which W is the work of the compressor, positive when the system delivers work and negative when we perform work on the system, and the latter is the case here. Q is the amount of heat added to the system, positive when heat is added and negative when heat is removed, which is the case here. As we know that 10% of the work is lost as heat, we can fill in all the values and we obtain the work of the compressor W, and this work is negative because we perform work on the working fluid. And the heat Q is also negative because heat is leaving the system. The second law of efficiency follows from the second law of thermodynamics for an open system in a stationary state. The entropy production S equals the mass flow times S2 minus S1 minus Q divided by T, in which Q is the heat transfer and T is the temperature at which the heat transfer occurs, and S is the specific entropy. We have all the information needed to fill in this equation and obtain the entropy production in units of kilowatt per Kelvin. The exergy destruction is T0 times this number. The first law of efficiency in the increase in enthalpy of the system divided by the work that was put in, and this is 90%. Of course, it must be 90% because 10% of the work of the compressor was lost in heat. The second law of efficiency is the useful effect, which is the work minus the exergy destruction divided by the exergy that was put in, which was the actual work. This second law of efficiency is computed at 78%. By systematically comparing and optimizing the first and second law of efficiency, we can design optimal heat pumps and refrigeration systems. To summarize our learnings, the second law of efficiency is defined as the ratio of the actual coefficient of performance and the coefficient of performance of the corresponding Carnot cycle. Exergy is the maximum theoretical work obtainable from an overall system and the environment as the system comes into equilibrium with the environment. Thank you for your attention.